Okay, so we today we're gonna quickly recap. I think what we learned about heterogeneous nucleation, and then move on to talk about the next stage for the solidification. Right. First, you nucleate a small solid particle, and this particle has to grow. Right. So nucleation and growth are the most two important processes for this solidification in a pure system. So we spend a lot of time talking about nucleation. We first mentioned homogeneous nucleation, which means that you have a let me increase this. Okay, we first talk about homogeneous nucleation, where you have the particle which are formed like, in the middle of this bulk liquid, right? And we know that in this case, we need to worry about several key terms in terms of energy change or energy reduction when you transform a small amount of liquid into the solid, right? The first thing is that if you replace this bulk or this small volume of liquid into solid, you reduce the free energy, because at a temperature lower than the melting temperature, the solid phase have a lower free energy than the liquid, right? But in the same time, you create also an interface. And we know that these two are going to fight with one another so that you have a critical size of the nucleus. And only for the nucleus that are larger than this critical size can further grow. And we talk about the Gibbs-Thompson effect, all those interesting things. So now and then we talk about the heterogeneous nucleation, right? The difference between heterogeneous nucleation and the homogeneous nucleation is that the former, which is a heterogeneous nucleation, in that case, instead of having a solid form within the bulk of the liquid, we have the solid actually start to form on the wall, on the bottom of the container, right? If you're holding a cup of water, you put it in the refrigerator, you induce a supercooling, you most possibly see that the ice starts to grow from the bottom of the glass or from the wall of the glass. It's rarely you see an ice start to form in the middle of the water. So that's exactly the same thing here. So this observation also suggests that it's much more easier for the transformation to occur in the or the nucleus to form in a heterogeneous manner than a homogeneous manner, right? So this also implies that because it's much more easier for the nucleus to form via heterogeneous nucleation, this has to indicate that heterogeneous nucleation requires a much smaller barrier for nucleation, and we work out the mathematical detail, or at least outline the way to work out the detail, right? So again, if we consider heterogeneous nucleation, we analyze a system like that, right? It's a little bit more complicated, but still, we can understand what's going on here. So I think the key here is, again, you look at, this small amount of bulk liquid has to be replaced by the solid, and you analyze what are the interfaces that has been created or the interfaces that has changed, right? So, and from this analysis, we see first you have this bulk free energy reduction because you have this amount of solid form, right? Replace the original liquid. So you have the reducer free energy, which is proportional to the volume of this small thing, right? And later we'll show that mathematically we can model this as a spherical cape. And then you have the liquid solid interface, right? Similar to the case that you have the homogeneous nucleation, because you create a small amount of solid and then you create this solid liquid interface. So you have to consider interfacial energy. And for the same reason, because you create the solid, so you actually create a new interface between the solid and the container. In here we call this mode. So you have the solid and the mode interface energy. And this is also increase of the total energy of the system. But the interesting thing is that, if you look at this interface, the solid and mode, you're not creating the interface from nowhere, right? Before you have the solid here, you already have an interface between the liquid and the mode. But when you have the solid replace that liquid, you simply replace the liquid and mode interface, but with the same area, right? So this means that, this is a new interface you created, but then you have to, take away the original interfacial energy, because that's not, totally going to be addition to the energy, right? Just change the energy, but you didn't change the interface. So that's why I have this minus term here, and this is going to be the total free energy difference if you have a small heterogeneous nucleus. And then we move forward to analyze some mathematical details for this system. So I think here is the key thing for us to reduce the mathematics. So we model this small nucleus. Sometimes people call this an embryo, as a spherical cape, which means that a part of the sphere, like this. So, and then, we can actually, so the one thing that we know is the key geometry of the spherical cave is determined by this angle theta, okay, which is complementary to this one. I think this is the same angle theta because this is a tangent line here. And the theta can be computed in terms of the interfacial energies, these gamma things, right? Because, at this point, we have the balance between all the surface tension forces, and the surface tension is essentially this particular interfacial energy form. So you have a very simple relation which we derived, and you have theta. Once you know the geometry, and you can easily use these equations, which I just paste and copy from Wikipedia, and the multiple sources you can get them, right? You can express the volume of the spherical cave in terms of either h or a, or the original radius of the sphere r, and by plugging all these geometry numbers, and also consider the relation between the three interfacial energies, we can actually simplify this total energy change due to or associated with the heterogeneous nucleation in this particular form. Okay, so and then we immediately recognize that within this parenthesis we have the expression for the free energy difference associated with the homogeneous nucleation case, right? So this is simply the bulk free energy reduction for spherical nucleus, and this is associated interfacial energy barrier or increase. But the difference here is that you have a factor which we call theta, S theta, which is a function of this form. Again, we can easily derive this by plugging all the expression for the mathematics, and you have a homework problem for this. But it's not difficult. It's just some simplifications, you can get this. Okay, and we show that the value for this guy is always between 0 and 1. Okay, so it's positive, but it's a factor that's always smaller than 1, but greater than 0. So this means that this means that in order to form the nucleus of the same radius r, right, and you have a much lower free energy barrier because of this factor. Okay, and then we basically move on and to look at that in a little bit more detail. So the basic idea is that first, if we do the plot for the homogeneous nucleation case, we have basically this particular form within the parentheses. We show this is a monotonic form. Initially, if r is very small, right, you have the surface energy that is dominant. So, increasing the radius from very small r can increase the free energy, and then reach a critical size of the nucleus, and further increase the size of the nucleus and decrease the energy. So that is for the homogeneous nucleation. And for the heterogeneous nucleation, you have exactly the same trend, right? It's the same curve, but rescaled by a factor of S theta. So it's just to bring down the curve, okay, or rescale the curve to a smaller magnitude for both positive and negative values. You'll see this is the new curve for the heterogeneous nucleation. And one obvious, two obvious observation here is that number one, because of the trend of because the curve for the heterogeneous nucleation is simply a rescaling for the one of homogeneous nucleation. Both of these curves have exactly the same location for the critical size of the nucleus, right? Because if you take derivative of this form of this curve with respect to r, it has nothing to do with the scaling factor, right? So they're going to have exactly the same location for the local maximum. This means that for both heterogeneous nucleation and homogeneous nucleation, if you impose the same degree of supercooling, right, you're going to have the same critical size of the nucleus. However, in the case of heterogeneous nucleation, this is also our second observation, for the same radius, right, of the nucleus, now it's just a partial sphere. It's just the spherical cave, right? But it's the spherical cave is associated with the same radius. For the same radius of the nucleus, you have a much lower energy barrier, right? So this means that this is the critical nucleus size, which is the same one as of the homogeneous case, but the critical energy is much lower, is reduced by a factor of S theta, right? And this one typically for many of the systems that we're dealing with is a very small number. So this means that you significantly reduce the energy barrier for the nucleus, right? And from our further analysis, we show that the nucleation rate is actually an exponential function of the energy barrier. So if you reduce this energy barrier, you get a huge increase for the heterogeneous nucleation, right? So you induce a very small delta T, this is the supercooling, magnitude of supercooling, and you can see a huge increase of the heterogeneous nucleus number of this nucleus. So that's why this is consistent with our observation, right? Because when you put a cup of water in the refrigerator, you're cooling the system gradually, right? Because the water is originally of the temperature of your room temperature. Now, if you put this in the refrigerator, so the temperature is decreasing, right? So it's first going to reach this particular supercooling, say -3 degrees Celsius, and you see a huge number of heterogeneous nucleus going to emerge in the system. And if the system is further cooled, and eventually you're going to see homogeneous nucleation, but this is going to be at a much larger degree of supercooling. Or if your supercooling is not enough, say I just stop at this temperature, and then you wouldn't see any homogeneous nucleation in most cases. So that's about heterogeneous nucleation. Again, conceptually, it's very straightforward. Mathematically, a little bit involved, but we have a practice for this, so I think you'll be fine with it. Okay, and that's basically the same. I went through this very quickly because we already seen this before. I just want to quickly give you a recap because I want to show you this very interesting example. That's really the juicy part. Okay, so I think we never had a chance to fully go through these two examples. But I think we did analyze this one, the second one, right? Because I know we have quite a few students from Intel, from semiconductor industry. So I'm showing this one, which is also from one of my own research project. So in this case, we're looking at a solder joint between two copper wires. I think this is a pure tin-based solder joint. We're taking out lead from the solder because it's not very environmentally friendly. So we're trying to understand if you take out this lead and put other more healthy elements into the tin, can we still try to maintain the same mechanical and thermal properties of the solder so it can still melt at low temperature, solidified quickly and as strong as before, things like that. But anyway, those know the key here. The key here is that I want to basically demonstrate some very important consequence of heterogeneous nucleation on the microstructure. Okay, so one thing you can clearly see is that this is a two-dimensional EBSD slice of the crystal structure of or sometimes we call this the color map for the crystal orientation or crystallographic orientation image. So each color of this region represent a particular orientation with respect to some reference system. But for now, I want to go through the details for the color map, but just to realize, each color represents a different orientation. So by looking at different colors, you can distinguish different grains. Okay, so one thing that I want to pay attention to is this region. Okay, where you see that in this region, the colors are kind of uniform. They're purplish blue, this kind of dark colors. But if you look at the morphology of the grain associated with these different colors in this region, you see that these grains are very elongated, right? It's quite different from this very big grain in here, or in here, up here. Okay, so they're very elongated, and it seems like that they're very like a needle, and they point to this direction. And you have some of those effects here, but much slower, much shorter. So the reason why you see these grains is because that when you probably this is a place where those melt solder first touches the copper surface, so it quickly starts nucleate and nucleate a lot of, because we have the copper surface, there always be some impurities on there. So those impurities are very nice nucleation sites, right, for the solid solder, tin solder, to form small grains. And then, so when the melt solder touches that, droplet touches that, and it quickly, nucleate a lot of small, solder, this solid tin nucleus, through heterogeneous nucleation, because it sees the surface, it can quickly nucleate in a lot of things. And then due to the temperature gradient, because you touch the surface here, right, and this part gets cooled very fast. So you have a large driving force for the small nucleus to grow. But because there's so many small nucleus forming here, so when they start to grow, they're kind of impingement on one another, they're squeezing one another. So the only way they can grow is to grow in this direction and grow very quickly. So as you see why they have this. Okay, this type of very elongated grain thing. But in the middle, you see this large one is probably because this one is not touching any copper surfaces, it's touching the air, so it has a much slower cooling rate, and it can afford to have probably a small nucleus to grow, and then expanding large size. On this side is probably, this is later that you added the other copper to. So at this stage, I think the temperature is already reasonable. So you just have a very small amount of nucleus, but still they're heterogeneous nucleus. You see, you see a lot of nucleus, but they don't have a chance to really grow very fast. Okay, so this is a kind of very interesting example for heterogeneous nucleation as manifested in the microstructure. And clearly, which is out of the scope of this class, that if you have a grains in this direction, this can significantly change the conductivity of the material and also change the impact, like the mechanical properties, as resistance to the impact. So heterogeneous nucleation is indeed very important, and this is not good microstructure, so we have to find a way to really control and optimize this. But again, this is a good example. So that's that. And a more interesting example is this one. Okay, so I like this example because it's not very easy to see something like this in Arizona. You have to drive to the Flagstaff, I think, and probably you won't see this. And I came from I spent 7 years in the East Coast, so I see a lot of these cool stuff there. So I think this is an example, which means that this, I show this example is clearly because this illustrates heterogeneous nucleation, right? So you have these, icy things that formed on the tree branch, right? So this has to be a heterogeneous nucleation because it used the tree branch, to, initiate the small nucleus. Otherwise, you just see this icy thing form in the air, right? And it drops down. So my question for you is that it looks like, this is very beautiful because you have all these icy stuff, kind of coating the tree branch, right? So my question for you is that I can totally tell you this is a heterogeneous nucleation, okay? But my question for you is that, if you think about these processes and think about initially, the nucleation processes, what has been nucleated on these tree branches? This is my question. So let me try to explain. So in here, right, we're working with the melt liquid solder, right, or solder alloy. So the thing that has been nucleated are the small solid, solder particles, and then start to grow in this particular case. Now, what has been nucleated in this particular system?
Moisture in the air.
Exactly. So it's not, it appears to be that we have a solid form, these icy things, right, on the tree branch. But if you think about it, initially, what has been nucleated is not solid. It's actually, first you have a lot of vapor, right, in the air, and the vapor nucleated into small water droplets on these tree branches. And because the temperature is very low, so these droplets, and then quickly, and within this water droplets and their heterogeneous nucleation of small ice nucleus, and then these ice nucleus then start to grow, and then you see this very nice, interesting thing. So this example actually illustrated two different types of heterogeneous nucleation. The first one is that vapor use the tree branch to heterogeneously nucleate into into water droplet on these tree branches. And then within the water droplet, small ice start to nucleate in a heterogeneous manner and begins to grow like this. So I think this is a really cool example of illustrate heterogeneous nucleation. Okay, so I think with that, this is all I want to tell you about the nucleation processes. Again, we have discussed the two mechanisms. The first one is homogeneous nucleation. And in this case, we talk about the driving force and energy barrier. And in particular, we discussed the critical size of the nucleus and then introduced the very important concept of Gibbs-Thompson effect, which is a very interesting and useful way of looking at how you connect geometry to thermodynamics in the case of nucleation. I will see that we're going to use this again and again in later analysis of the growth and in other applications. And then we talk about heterogeneous nucleation, which is just an analog of all these things we talk about. So that's about nucleation. Okay, so this is, I think we're good about this. And then I'm going to switch gear, okay, and talk about the growth, which is even more interesting. Okay, so let me start sharing my screen. Okay, so this is a solidification in pure system. Okay, so now we're talking about the growth, right? So there are two steps, again, as we said before, for solidification. The first one is, you've seen this for many times. I'm sorry for if you think it's too boring, but I think this is a very good animation to show the two processes. So first you have the nucleation. I think we're very clear about this processes. And once you have the the small, solid nucleus form, and we have to worry about the growth, right? How you add more atoms to the small nucleus. So this is the key processes we're going to focus on for this class. And in particular, yes, so we talk about the concept of solidification, in particular, the growth of the nucleus in pure system. And in this context, we can analyze the propagation of planar solidification front. Um, and then, as you probably can imagine, now the propagation of planar solidification front is going to be a highly ideal case, and in reality, you're never going to have things going to remain to be a plane, right? You have some instability, you have small bumpy things form, and we're going to study the condition for the stable and unstable growth of the planar front. And in this case, we're going to see again our good friend Gibbs-Thompson effect and play a key role in determining the instability. And this is going to induce a perturbation wavelength selection. So I'm pretty sure that you see these type of things. You see that like in this very nice snowflake things growing in the form of a dendritic type of pattern, right? You didn't see the snowflake grow like in a perfect, hexagon shape or perfect polyhedral shape. Definitely not a spherical shape, but it has this very branch type of different type of branches going through in all directions, like this one, or even here you see these branching type of growth. We call this dendritic growth. And why you see that, why this thing tend to form dendrites, is because of the Gibbs-Thompson effect. And this is going to select a very small a proper a radius for the tip of this thing and further grow. So that's going to be the kind of overview for the topics. And I don't think we can finish all of this in this lecture, but we'll try to see how far we can go. But definitely we can finish this, within this week. Okay. So yeah, so so basically, let me see. Yes. This is again the same picture that we have seen before, right? So we have a small nucleus form in the system, and if this nucleus is large enough, right? So larger than R star for the associated supercooling, you see that during after the small nucleus form and after some time, this nucleus tries to expand a little bit, right? So this dashed circle highly schematically illustrate the later stage of the nucleus. So you initially have the nucleus, and after some time, you see the nucleus grow, right? But we're not looking at the whole nucleus. For now, we just sort of zoom into a very small or tiny portion of the nucleus. Okay, it's like if you consider nucleus as Earth, where we're at ASU, we're just thinking that we're looking at this ASU. So locally, everything looks like a flat thing, right? So that's why we can talk about the so-called planar growth, is because we're looking at very local things. Because even if the nucleus is very small, in our eyes, in our naked eye, probably cannot even see them. Like there are few microns or 100 nanometers in size, but in terms of compared to an atom is pretty large, right? So if we're an atom and we're looking at this a small region of nucleus, is all looks like a fairly like a flat thing. A flat thing to us. So that's why we just mathematically take a very small portion of the nucleus out and consider that this is locally looks like a very flat interface. Okay, so and then we start from now on, we're going to focus on this particular small region of the interface, right? But don't forget that it comes from a large portion. It's just a very small portion of the whole nucleus. But anyway, so let's focus on this guy. So what I'm looking here is that I focus on the solid liquid interface, right? I take this part to be the solid. I try to use the same color for the liquid. Let's just think it's transparent. Okay. So if you look at this particle, if this nucleus start to grow, right? Now this means that this we call this the solidification front, which is the interface between solid and liquid, right? Now, in order for this guy to grow, you see that this front has to propagate further into the liquid phase, right? Does this make sense to everyone? Right? So this propagation, okay, the propagation of this flat or planar solidification fronts into the liquid correspond to the growth of the nucleus, right? I think this is pretty clear. And then there are different ways that you can basically induce the propagation of the solidification front or the growth of the nucleus. But in our case, we consider an ideal case that we keep the solid at a fixed temperature, which is the melting temperature, okay, and then we induce a supercooling in the liquid, right? This is kind of the easiest way to implement, because you can always control the boundary condition of this liquid, right? You can impose particular temperature at the boundary, and then far away from the nucleus, you can basically imagine that at the nucleus, because we have the solidification occur, so the temperature has to equals to the at this flat interface, right? It has to equal to the melting temperature. But for, if you move away from this solidification front deeper into the liquid, we're gonna get a decrease of the temperature, because far away from this solidification front, you induce a very high supercooling, right? So assuming that we have just a linear decay of temperature, so this is the temperature profile you see in the liquid. Okay, does this make sense to everyone? So basically, we're establishing a coordination system, right? We're imagine that we have a axis along the horizontal direction right here. So this is my x-axis, right? We can use this axis to denote the location of my solidification front. And then in this particular case, the y-axis simply give us the temperature, right? In the liquid, we have a uniform temperature, which is equal to the melting temperature. And I'm sorry, in the solid, we have the uniform temperature distribution. And in the liquid, we have a decrease of the temperature, okay, because we impose supercooling. That's basically the setup. Any questions on this one? Okay, so now if not, let's consider. Okay, this is an interesting case. Now let's consider, what happens if the solidification front propagates a little bit. Okay, so what do I mean by propagation of the solidification front? Okay, it's not that the whole particle is moving in this direction. It means that the particle grows a little bit, right? So by propagation of a solidification front, what I mean is that I have a thin slab of liquid, right, which originally is liquid, and now this liquid transforms into the solid, right? So in this way, I propagate my solidification front a little bit to the right or into the liquid. Does this make sense to everyone? Okay, so so how can I define a velocity v? So this is very straightforward. So suppose this is my original position of the solidification front, right? Now, say I monitor the system. Suppose I induce the correct condition. So during time dt, during this small time, okay. Now, if I see that I have a very thin slab of solid form, and the thickness of the slab is dx, right? So I can easily define a velocity, which is dx over dt. Okay, this is how we define the propagation velocity. Okay, but meaning of this is that, during time dt, I have, a small amount of liquid transform into the solid, and this add to a thickness of dx to the original solid front. So v is simply defined as dx over dt. Does this make sense to everyone? Okay, so now my question for you is that, okay, what happened to the system if I have a small amount of liquid transform into the solid? Or in general, what happens, in terms of the energy of the system if I have some liquid transform into the solid? Does the system release heat or absorb heat, or do something along those lines? If I have water, freeze into ice, what does the water do in terms of energy? The water, it release heat, right? So the water has some extra heat. I have to throw these heat away, right? That makes sense, because if you look at water, it has a disordered microstructure, right? What is heat? Heat is the difference of the entropy. I'm sorry, the enthalpy, right? So if this is the enthalpy of the liquid, if this is the enthalpy of the solid, at the melting temperature, which one is going to have a higher enthalpy, the liquid or the solid? What determines the enthalpy of the system? We have this in a midterm exam. At this stage, we should be very clear.
The number of bonds.
The number of bonds, the quality of the bonds, but eventually this is going to go to the microstructure, right? So in the water, what is the key thing? What is the key type of bond contributing to the enthalpy? What is the interaction between water molecules?
Is it the hydrogen
the
bonding?
hydrogen bond, right? And in a we if you compare a disordered packing of these water molecules versus a very ordered network of the water molecules like in the solid, which one gonna have more hydrogen bonds? The solid, right? Because this is an ordered way. So basically, this means that every possible size for hydrogen bond, it guarantees that you can have one there. So it has a much better, because it has ordered structure. So it has a much larger number of high quality hydrogen bond compared to the liquid, right? And we know that if you have this good bonding between the atoms or molecules, it reduces the energy or reduce the interaction energy of the system. So if you compare the enthalpy of liquid and enthalpy of solid, which one has a higher enthalpy? Which one has a higher energy due to interaction?
The
Solid.
solid.
So the hydrogen bonding. So if we have atoms, right, these two atoms form a bonding. Does this reduce energy or increase energy? Compared two atoms are free. This bonding it induces a lower energy, right?
Reduce.
It reduced energy, right? And in here, you see, if you compare number of bonds, in here, you have much less hydrogen bonding, right? And in here, you have a lot of hydrogen bonding. So which one have a lower energy? Has interaction energy. The solid has a lower enthalpy, right? It has a lower interaction energy. Does this make sense? I think at this stage, we should be very clear about this. Okay. So
it's going to be endothermic.
I'm sorry, what's that?
It's like an endothermic release.
Yeah, release
energy.
exactly release, right?
Okay.
So because you form bonds, right? So there's some extra energy of the atoms that has to release because when they form the hydrogen bonding, reduced energy of the system, right? So when water in a liquid form transform into ice, which is the solid form, it release energy, right? In form of a heat. Does this make sense to everyone? But all of these are consistent, right? We know this as a fact because if you freeze water into ice, it releases energy, it releases heat, right? But this is why, because water in the form of liquid has a higher enthalpy than the solid form, and for the reason we were mentioning. So that's why you release heat. Okay, but the whole thing that I want to get out is that if I have a small slab of liquid transform into solid, it actually releases heat. So you're going to have some heat generated in this area. Okay, this is what I want to share with you. Does that make sense? So this is a consequence, right? So if you want to make a small amount of or small slab of solid from the liquid, you have to pay the cost of what? Releasing a heat, right? Amount of heat here, which we call dq. Does this make sense to everyone? Okay, so let's think about, okay, we want this process to be continuous process, right? We didn't want to, the solid and the liquid to be equilibrium. If we want the solid and liquid to be equilibrium, the particle won't grow, right? This small nucleus won't grow. So we want the nucleus or the solid to keep on propagating with a constant velocity. We call this a planar growth, right? Or steady state planar growth. So, and then we have to worry about the heat, right? So what do I mean by that? If I just do not, we know that if you form a small amount of liquid, the small amount of liquid transform into the solid, but like here, right? So if suppose that now I fix my temperature to be this, okay? So in the liquid and in the solid, I have the same melting temperature here. Okay, I know that there'll always be some solid particles adding to the molecules added to the solid surface, and it can form this small amount of solid. But if we have the system, like in the liquid and the solid, they have the same temperature. What does this mean is that, the heat gonna go nowhere, right? Because, like in the case of diffusion, you have to induce some gradients of temperature to take heat away. Now, if I have the liquid and solid keep at the same temperature with no gradient, and even if I have a small amount of liquid transform into solid, okay, it's gonna generate heat. But if the heat is not sufficiently dissipated or taken away, what's going to happen to this small form, with this new slab of solid just formed? Is this a clear question? I'm just trying to illustrate the key things that we have to key conditions we have to maintain in order for induce this very stable steady state growth for the solidification front, right? Suppose we do not have any temperature gradient in the liquid, okay, and suppose we can still transform a small amount of liquid into the solid, but we know this is going to generate heat. Now, if the heat is not taken away, what's going to happen to the system, even if we have a small amount of liquid transform into solid? Will that small amount of solid be stable?
No.
No, right? Because the heat is still here, right? So it feels a lot of heat in this thing. So this small amount of solid will not stable. So if you're not taking the heat away, what's going to happen to the system is that this thing gonna absorb these extra heat in the system, right, locally here, and then melt back into the liquid. Okay, so in this case, if you do not induce any temperature gradient in the liquid, the solid will not grow. Well, it's just remain to be stable like that, but it's a kind of a dynamic stability. But on average, it won't grow. It will constantly form and melt, constantly solidify and melt. And if we have no, loss of this extra amount of heat. Okay, so basically this illustrates, you have to really take away the extra amount of heat in order to induce a very stable growth of the solidification front in that direction. That whole analysis makes sense to everyone? Okay, so that's why we see this. Okay, so that's pretty much the key physics that we have to appreciate here. Now, if we understand this point, okay, yes, so if we understand this point, the subsequent analysis is very straightforward. So the thing is that if you want to form, you want to induce a steady state propagation velocity of a solid, this means that you're constantly transforming the liquid into solid, right? And this is going to generate heat. So in order to maintain that particular solidification processes to occur at a stable rate, we have to continuously, heat is continuously generated, but we have to continuously take away the heat, right? So that, you can have more solid form and the heat is taken away, the solid is cooled to the melting temperature, and you keep on doing this. So that's the, a key condition to maintain. And assume that in our analysis, in our system, we can impose proper boundary conditions such that it's going to give you a very nice temperature gradient, which is just large enough to take away this extra amount of heat. Okay, so and to induce a growth velocity v. Okay, now the key thing is that what is by just enough, right? What are the mathematical relation for us to relate the temperature gradient and the growth velocity and all of these things together, so that if I were to do this as experiments, I can actually impose proper control of this solidification processes, and that will be the key for our subsequent analysis. Okay, so yeah, so basically now what I'm doing here is to make what we just discussed in a little bit more quantitative way, right? So suppose now, we have this solid, right? This is original solid, and we have a very thin slab of liquid transformed into solid, which is highlighted by the pinkish, thin slab here. And we assume that the solid is held at a temperature of Tm, okay, melting temperature, and we induce the temperature gradient, which we later call dt over dx. Okay, this is for the liquid. And now first we need to write down the amount of heat generated during this process, right? So that is basically given by, let me see, this LV is the latent heat, which is basically the difference of the enthalpy for the liquid and solid state at a melting temperature. That's the same thing, but typically we call this latent heat because we can measure this experimentally. And it's the latent heat per unit volume, okay, LV. Okay, and A is the area of this small this liquid thing. Okay, it's kind of a vague concept, but just imagine we can define area for this thing. Okay, so it's the area for this guy, and dx is the amount of the or thickness of this very thin slab of solid that just transformed from the liquid. So all together, the area times the thickness, you're going to get the volume, right? And because LV is the latent heat per unit volume, so altogether, this gives you the amount of heat that released due to the transformation of a small region of liquid to the solid, right? Does this make sense,
Professor,
everyone? Yes.
we assume that this area is very small so that it's flat, and now we assume it's very large, then dx.
No, we didn't assume it's large. So I understand what we're talking about. We assume this is small, so we can imagine this is a flat. So, but this small is like intermediate range of small. So suppose the nucleus we're looking at is on the microns, right, or several microns, or even like 100 microns. This is still small nucleus, which we cannot see by eye, but it's quite large compared to atomic size, right? And this region is, think about this region is about 100 nanometer. Okay, that makes sense. So this 100 nanometer is much smaller than the 100 macrons, right? So we can basically consider this as a flat compared to the overall nucleus, but it's still much larger than the atom, which is just a few astron. Does this make sense to you?
Yes, yes.
Yeah, so it's kind of an intermediate range, but this is a good question. So that's that, right? And but I don't think this is gonna complicate anything. Dx is just like say this, if this is 100 nanometer, right? And dx may be just a few nanometer compared to the overall size. We can still call this small, but it's still much larger than atomic size. You have thousands of or even millions of atom added to that, right? Because you have a volume. So I think this is okay. Okay, so that's that. And we already said that the dx, or the relation between dx and v, is given by this, right? So we consider this occur during time dt, and then through this we can define the propagation velocity we call v, or we can express dx as v times dt. Okay, but remember dx is simply the thickness of this small slab of solid just formed from the liquid. Okay, so this is the heat, right, generated as we already analyzed, but also we mentioned the heat has to be taken away, right? And what is the mechanism that we can use to take the heat away?
Convection.
Conduction, right? So because this is not a class about heat transfer, but we know that there's three ways that you can take heat away: radiation, right, how we receive heat from the sun; and convection, that you have a hot water, you want to cool down a little bit, you just stir it so that it has convection with the air in a very complicated way; or simply conduction, you just have a cup of water in there and you just hold it still, so eventually the heat is going to be taken away very, very slowly through the gradient, right, the temperature gradient built in the surrounding air and a cup of water, right? So this is three different ways for taking heat away. And in our system, we'll use conduction because there may be some radiation as well, but the main mechanism is conduction, because we definitely don't want to stir the liquid during the solidification, because if you stir the liquid, you're going to create a disaster of the microstructure. So we just wait for a little longer time, but wait the heat to slowly dissipate it away through conduction. Okay, but if you take any heat transfer classes, and if we're talking about heat conduction, you realize that the mathematical relation between the heat flux and the temperature gradient is exactly the analog of the Fick's first law, right? So even if you didn't take this class, that when we talk about diffusion, we mentioned this at the end of our lecture. So mathematically, the conduction of heat is very similar to the transport of atoms through diffusion. Okay, we have virtually the same type of laws. The reason why for that is because all of these conduction or transport is kind of a first order approximation. So you're always going to have the flux is proportional to the driving force, and the driving force is the gradient of some potential field. The reason why is we're looking at a linear first order dynamics. So we see a lot of mathematical similarity between these things. But anyway, uh, so if we agree that or which is also the fact that in this system the heat is taken away by conduction, right? So and then there will be a heat flux, right, and that we can define, which is basically the amount of heat that be taken away or through a unit area per unit time, right? So and then you can easily then convert the flux back to the amount of heat by multiplying the area, which is the area for the system, and then during time dt, right? This is by definition the flux, right? Flux is amount of heat per unit area per unit time. So when we multiply this two quantity back to the flux, you get amount of heat. Okay, so and we know that if you want to impose a steady state growth, this means that this heat has to be taken away sufficiently quickly, right? But just enough from the system. So it means that during this time dt, I propagate by dx, I generate this amount of heat dq, and this dq is just the temperature gradient is just enough to take that dq away. It's not too high, it's not too low, it's just enough. Okay, so this dq here, which is the heat taken away by the temperature, by the conduction, is the same as the dq generated by forming the small amount of the solid. Okay, so that's the consideration. No, the heat, I got a question that is the solid, liquid, both taking the heat? No, it's only the liquid taking the heat. The reason why is that we're setting this up because we're assuming the solid has a fixed temperature, which is the melting temperature, right? So there's no temperature gradient, and this means that in the solid, there's no way to take heat away. So we only consider heat is conducted through the liquid, which is easy to control, right? Because you can control the boundary of your container to impose different temperature gradients, but you cannot easily control the nucleus, right? So that's the reason why we have this assumption. But again, this is assumption, right? In the real system, it's much more complicated. But let's move on. Let me see. Yep. So yeah, and then this is basically, we know these two heat has to equals to one another. Let me see. I got one more question. Yes, in reality, the solid might be colder, and there's another scenario that you can have solid colder than the liquid. But again, we just set up the problem like this because we can analyze the key mechanisms clearly in this example. But in the real case, the solid might be colder, but that will make things much more complicated. But in here, we just use this example to illustrate the key idea. Yeah, but in general, you have much more complicated and different ways of the temperature profile, which all change how the microstructure can evolve. Yeah. Anyway, let's yes.
Can I ask a quick question?
Sure, go ahead.
So I know, like, if you have a pot of water on the stove and you're heating it up right before it gets to the point where it goes from liquid to like a bunch of steam coming off, you can actually see convection, like swirls in the water. So is that, I guess, different from what we're talking about here on like really tiny scale? Because I was figuring that the temperature gradient creates like the swirls or the vortex, and that's what pulls the heat away.
Yes, you can have that things happen, but this is related to, there are a lot of factors affect this. Number one is that the viscosity is a very important thing for that convection flow. So the water, you see that because you can easily see this in the water because it has a very low viscosity. It's kind of viscosity means how sticky the liquid is. In the case of hot melt, for most of we'll use this water as an example, but this might be a little bit confusing. But in most cases, like in a real alloy or ceramic materials that we're dealing with, or even polymer materials, the hot melt is very, very sticky. It's very viscous. So in those cases, I think also the temperature gradient we impose here are I'll say relatively small, because if you impose too large temperature gradient, you're going to cause unstable growth so very easily. We don't want that in this case. So consider all these things. In the system we're analyzing, the conduction is the key mechanism, and we ignore. There might be some small convection locally, but again, in our analysis, we just look at the most straightforward, simple mechanism, so we can appreciate the key physics here. So that's but all of the scenarios we mentioned is quite possible. But I would say that compared to the conduction, and if you can carefully control the thermal conditions for those processes, we can make sure the conduction is the key mechanism.
Okay, that makes sense. Thank you.
Thank you. That's a good question. So yes, let's keep on moving. Yeah, all those things I think are very important in the real kind of solidification applications. But again, like for the scope of this class, we're setting up a very simple ideal scenario, and we understand the key things in that ideal scenario, and then we start to add complication to that. So now we're still at the very early stage of the ideal scenario. But let's finish this first. Right. So that's the this is the heat generated, and that is the heat that is taken away by the conduction, right? And then if we look at a little bit further into the heat flux, as we said before, because it's a first order dynamics, so the heat flux is proportional to to the temperature gradient, right? This is very much like the concentration gradient, and K is the conductivity, the thermal conductivity. This is the analog to the diffusivity, right? If you're talking about diffusion, okay? So again, you see this is basically very similar to the Fick's first law that we are already familiar with, right? But it's just in the context of heat conduction, okay? So now if we have this flux, this explicit expression for the flux, we can plug this back into the expression for the heat conduction equation, right? This is again the heat taken away by the conduction. And then we have negative sign here because again, the temperature gradient is negative, right? But the heat taken away is positive because it generates heat, release heat, right? So, and then times A and dt, okay? But the sign here is just to realize that dt dx is negative. I think later I changed this to absolute value, so I dropped the sign. But that's the kind of tricky thing. Just I want to make sure that we're clear. Okay, so for the steady state or stable growth of the planar interface, right? The heat generated for making the thin slab of solid is just equal to the heat taken away via conduction in the liquid. So based on this condition, now we can write down the expression for, this is the same amount of heat, and this is generated by the solidification of the thin slab of solid, and this is the amount of heat taken away by conduction, right? We write down these two equations together, and we can clearly see that this area cancels one another, right? And if we can take dt to the left and take this LV to the right, we rearrange the term a little bit, and we have this velocity, okay? Because now on the left-hand side, we have dx over dt, which is the propagation velocity. And then on the right-hand side, we have these two terms. This is k, which is the thermal conductivity, over LV, which is the latent heat, and then proportional to the temperature gradient. And you can just add an absolute sign here to just worry about the magnitude, okay? And I think it's probably easier to imagine this. But the reason why we have a negative sign here because temperature gradient again is negative. Okay, so that's basically expression. Now let's look at this a little bit more detail. So so if you look at the right-hand side, the left-hand side is the velocity, right? Propagation velocity. This is something that we want to control, right? So like in a solidification processes, if you're interested in how fast these particles can grow and how fast you can complete the solidification processes, we want to impose some conditions. Okay, as I said before, the conditions we typically impose is the temperature gradient, right? Because you can impose some boundary conditions, assuming everything is good enough, you can, in principle, calculate or at least, estimate the temperature gradient in the system or, in the vicinity of the nucleus. But anyway, so and we look at several factors that affect the solidification velocity or the propagation velocity. So first, if we see that the velocity, if we fix all the other factors but just increase the conductivity, okay, what do you see? You will see an increase of the velocity, right? This means that it increased the conductivity of the liquid, which means they changed the material, right? But suppose that you can increase the conductivity of the liquid, this is going to induce a much faster growth of the solid. Right? Does this make sense to everyone? Yeah, I think it makes sense, right? Because this means that, you can generate the same amount of heat, but because I have larger conductivity, this means that, I can more quickly, in principle, take the heat away, right? This means that I can afford a much larger growth velocity. I wouldn't have the heat that, the generated heat are piped up in that region, but not taken away. But because you have large conductivity, so I can quickly take those heat away, and I can in principle induce a larger velocity. Right, so this is reasonable. And if you look at LV, right? So what is the role of this guy playing here? So if you have a larger LV, this means, if you generate the same amount of solid, you release more heat or less heat. If I have a larger latent heat, right? This is the amount of heat released per unit volume. If I have larger latent heat, so if I generate the same amount of solid, if my latent heat is larger, this means that the heat I generated for transforming the same amount of liquid into solid is larger, right? Does this make sense to everyone? So this means that more heat is generated per unit volume, and I have to, either spend more time to take it away or do something else. But in general, I don't like this because if I have more heat, this extra heat gonna slower down the growth of the front, right? So that's why we see this is inversely proportional to the latent heat, which means that if you have a larger latent heat, the velocity is gonna be slower, okay, smaller. And then finally, this is something we can control. The first two things is not really we can really control. You fix the system. Say I work with water, or I work with melt iron, I work with copper. Once you fix the material, it's basically fixed, right? But the temperature gradient is in principle something you can control, as I mentioned, right? You can induce different boundary conditions at the wall of the container. And then through this way, in principle, you can control this. So, if you have larger temperature gradient, clearly you can have a faster grow, right? Because it has a faster, because this is a driving force for the transport of heat. So if you have a larger gradient, in principle, you can induce faster heat transfer. You can take the heat away more quickly, and this will lead to faster growth. Okay, so that's pretty much the steady state growth of planar interface. Okay, so that's I think all I want to say about these processes. Again, it's very conceptually, I think is a very straightforward. We just analyze the scenario where you have this planar interface and a small amount of liquid transforming into the solid, and by considering this balance of heat generated and heat dissipated, and consider the first law of conduction for the heat, we arrive at this very nice equation for the velocity. Okay, and we show that this propagation velocity is proportional, is related to three factors: the heat conductivity, the thermal conductivity, latent heat, and temperature gradient. And we understand the role of these things very, very straightforward. Okay, so that's that. Okay, now, any questions before I left of this? I think this is very straightforward. So now let's look at, so we mentioned that is the keep this system to be at a planar propagation is really the ideal case, right? Because in reality, I don't think you ever see a small nucleus remain to be a nucleus of a planar interface. If this is the case, you will see all the snowflakes going to have a perfect hexagon shape, or all of the solid form in the liquid going to have a beautiful polyhedral shape as they grow, and you're going to see those polyhedral shapes as a large particle, not just a small nucleus, but you never see those. So this means that this planar growth scenario probably going to work in the beginning stage of the nucleation and growth, especially the initial stage of growth. But it went dominant the full stage of growth, right? So what happens, and as you see that in most cases, you see that as the snowflake grow larger and larger, you see a lot of these branches forming, these dendrites forming, right? So this means that instability gonna kick in at some stage of the growth process and take over and become the dominant mechanism for the growth. Okay, so that's just what we can analyze now. Okay, so and so this is kind of leads to the scenario for the unstable growth, right? So so in the ideal case that you have a planar interface, right, and all the atoms, just liquid atoms, just constantly and uniformly added to the solid, so you have a thin layer uniform thickness, of solid form, right? But remember, in atomic level, everything is gonna be fluctuating. There's guarantee that I have the exactly same amount of atom adding to this area versus this area versus this area, right? There always be some fluctuation, so that after some time I may have more atoms adding to this area, leading to a small bump or bumpy or small bump, right, on the planar interface. Okay, so why it has this small bumpy thing is because of fluctuations, right? Because when the atom adding to the interface, to the solid, there's no guarantee that you have exactly same number of atom adding to the exactly same amount of, to the area, to the same area. You always have a little bit more atom, to some areas than the others due to fluctuations, right? I think this is very understandable. So and the consequence of this fluctuation is that you're going to have a small bump on the planar interface. Is this clear to everyone? So we're not interested in exactly how this bumpy area form. We're just interested in that if you already developed this small bump, whether this thing going to further grow into a branch or a dendrite, or this thing going to melt back into the planar interface, right? So there are two consequences. There are two possible outcomes. If the first one is this thing going to further grow, and the other one is going to melt back. Okay. So now in the case that this thing melt back, okay, this means I can always have the a planar interface, right? Because this perturbation is not stable. Or in the other hand, if this thing turns to grow further into the liquid, okay, we're beginning to produce a dendrite, right? Because this small bump begins to develop into a branch and is further going to grow. So there are two scenarios. Okay. Now, again, these two outcomes are equally possible depending on what is the temperature profile in the system. Okay. But in this particular class, if we consider, like in this particular scenario, if we consider the heat is taken away from the liquid, which means that you have this type of temperature profile. Okay. So in the liquid that, we have a continuous decreasing of temperature. Okay. That is our context. Now, in this context, do you think that if I form a small bump in general, okay, this thing would like to further grow into the liquid, or it's going to melt back so that you're going to have a planar interface that is stable? Is this a clearer question?
Can you repeat it one more time, please?
Okay, so we're talking about this small bump on the surface, right? So, and we don't care how it forms, okay? We just to say, suppose that now I have this small bump already formed on this solid, right? Or on this solidification front. And considering that in our scenario, the heat is taken away from the liquid so that we have this, temperature profile in the liquid, which, as you further move away from the solidification front, you have a lower temperature. In this particular context, if I have, or this particular system, if I have a small bump form on the solidification front like this, right? Is this thing, this small bump in general, going to further grow into the liquid, or are you going to melt back so that you're going to maintain to be a planar interface?
I would guess that it would continue to grow.
It will continue to grow, right? So, we don't have to, really, I think I have a typo here, but anyway, so I think that the idea is very straightforward, right? Because, the whole thing is that, when it forms this small bump, we need to basically say whether the small bump will be stable or not, right? And in this particular cases, okay, what determines the stability of the solid? The degree of supercooling, right? So if it feels a supercooling, if it invades or intrudes into a colder region of the liquid, okay, in general, I would say this guy gonna feel a larger supercooling, right? So in general, I think it will grow. So this is our tuition, right? So, and it turns out this is exactly the case. So if you have a small bump that protrude into the liquid, now because the liquid has a lower temperature, see here, the further you go into the liquid, the lower temperature you feel, right? So if you have a small bump things developed on the surface and protrude into the liquid, it feels a lower temperature. It go, kind of get into a colder region, so it feels happy, and in general it will grow, right? And the second thing is that not only the temperature is lower, if you have a small bumpy surface here, right? And these dashed lines shows um, these are equal temperature lines like that. Basically, the lines give you an idea of the temperature gradient. So when we have the surface that go like this, it kind of squeeze this equal temperature line a little bit, okay? And this is gonna basically make this distance smaller, which means that you have a larger temperature gradient. So this, again, if you compare this velocity, we have a slightly larger temperature gradient. This means that not only this guy is happy because it's in a colder region, and it also potentially going to have a faster growth velocity because on the tip, it feels a larger temperature gradient. So the velocity of the growth is going to be faster. So this basically these two reasons, which are just intuitively we get, okay, all pointing to the same direction that in this particular system, if we choose the temperature gradient in the liquid to be like this, and if you have a small bump form on the surface of the solid, it will further grow. Okay, does this make sense to everyone? So again, this is very intuitive, but it's related to what we described about the propagation of of the solidification front. Okay, so this is our intuition. I think we're okay on this. And the next thing we need to do is to really, so before I go through this slide, I think it's gonna be the tricky slide. So there's one thing that we didn't really, pay attention to is the fact that this bumpy surface has a curvature. Okay, so now both these two, okay, are plus, right? Because if you have a bumpy surface, a bumpy small bump here, and we know that it's protruding into a colder region, which make it happy. And also this is going to increase the temperature gradient, which means that it potentially going to give you a larger growth speed, right? So this thing going to further propagate. But what is the negative effect? What is the bad thing about the bumpy surface? It has a curvature, right? So if you have if it's a bumpy surface, it has to have some curvature associated with compared to the flat propagation or flat interface. And we know that whenever you have a curvature, you're using energy, right? You're using the overall free energy reduction to overcome some extra surface energy. Does this make sense to everyone? So whenever you have a small, curvature, this means that you have to worry about the Gibbs-Thompson effect because you have to use some of the degree of supercooling to overcome your extra interfacial energy. Okay, so this is the negative part about this, right? So that's why I use the word generally. Okay, so let's forget about this negative part, but in general, if we just have this, I think the two positive part are going to dominate for most of the cases, and you see this happens. But don't forget that we have a curvature here, so we have to, if we want to understand the mechanism correctly, we have to go back and ask about, how the Gibbs-Thompson effect can play a role here. Okay, so that's what we're going to talk about. But I seriously doubt that we can finish this. So are we clear about this? Is this idea clear enough? Okay, so let's try to move on. We still have 5 minutes. Let me try my best to see how we can do about the Gibbs-Thompson effect. I don't think we can really reach to the point that we derive the full equation, but at least I want to reveal the Gibbs-Thompson effect. I think that's just what I can do. So now what is Gibbs-Thompson effect? I think this is the third time that we have seen this, right? The overall idea is again that we convert the knowledge of the geometry in terms of curvature of the nucleus into some thermodynamic considerations, in particular in this case, the degree of supercooling that felt by different particle. Okay, so let me revisit this again, right? So if we have a particle right here, I induce a supercooling called delta T, right? And then this, so I fix the temperature of the system to be T star. Okay, and then, I know that at this temperature, I can produce nucleus of different size. I can have smaller ones which are not stable, and I can have this one R star, which is just as stable given this supercooling delta T, right? And I have a larger nucleus, which I call R2, okay? So now my question is that, okay, at this particular temperature T star, what is the effective supercooling this particle R star felt? Is this a clear question? Are you still with me? Or you think we already have a lot of information? If you think we have too much, I can stop here. So my question is that, we set up this problem, right? So we induce the supercooling delta T in my system, and I fix my temperature to be T star. And by the way, T star equals to the melting temperature minus delta T, right? This is in the exam. Okay, this is my T star. My question for you is that if I look at this particle R star, right? What is the effective supercooling that this R star feels?
He feels colder, correct? Because T star is lower than Tm, and the amount of supercooling is delta T.
Yes, the amount of supercooling is delta T, but this amount of supercooling is with respect to what system? Let me answer my last question. So if I have a system with infinite large nucleus, which means that I have a planar solid, right? I have no curvature at all for the planar solid. This particular thing feels a supercooling of delta T because its melting temperature is Tm, right? For a planar solid like this guy, right? Its melting temperature is Tm. And now I decrease the temperature further to T star. Okay, so this guy gonna feel a supercooling by delta T because the actual temperature is by this amount of lower than what I need for the melting temperature. But how about this guy? What is the effective melting temperature for this Re star?
Zero.
The effective melting temperature is T star, right? So the effective supercooling this guy felt is 0. Does this make sense? I think it's, again and again, we're visiting this. Why is that? Because if I have a planar or an infinitely large nucleus, right, I have this delta T as my supercooling because I have this delta GV as my reduction of the bulk free energy. But for a nucleus like that, I don't have any advantages in terms of the free energy anymore. Why? Because I use all of the extra reduction of free energy to overcome my interface energy, right? So I use all of this energy to overcome my interface energy. So at this stage, I don't feel any supercooling at all. I'm just marginally, critically stable at this point. My melting temperature is T star, and my current temperature of the system is also T star. So this R star feels no supercooling. Okay, so I guess I'll just stop here, and we're already at the time, but I'll stop here, and in the next lecture I think it worth to revisit this again, because in here we're gonna use the Gibbs-Thompson effect to understand what are the supercooling felt by each of the particle. Okay, and then we're gonna see how this is gonna play a role in determining the growth for these different bumpy surfaces, because if you have smaller bumps versus large bumps, which one going to be more stable and which one going to grow faster? It's the interplay of the degree of supercooling versus temperature gradient versus a lot of things. But Gibbs-Thompson effect is clearly the first step to understand this. Okay, but for this class, I'll stop here, and in the next lecture, we're going to start to pick up from this Gibbs-Thompson effect. I'll revisit this effect again, so don't worry about that. Okay, so I'll stop recording.